Should I start? Hello all, welcome to our live problem solving session. We're going to solve the exam from last year, and I will start with the first question. The first question is about Boolean algebra, and the question description asks you to complete the truth table first based on the description given in the question, and then kind of do some simplifications. First, let's start with the truth table. The problem explains that you have 4-bit inputs and you have 2 different outputs, and then the first output is factorial, which is only 1 when the input number is a product of all positive integers that are less than or equal to the input number. So it's a bit of a complex description for 0, but for the solution for 0 is given, so we have to go through the next. So the second entry is 1, and 1 is a multiplication of 1 and then all the smaller positive numbers, which is none. So this is 1 for factorial. And the second input is 2. 2 is a multiplication of 2 and 1. So this is also 1 for the others. And if you go through the same description for all the other numbers, you will see that it's never the case for any other numbers. So all the entries should be 0 for the remaining ones. And then the second output is called D4, which is only 1 when the input 4-bit number is divisible by 4. And this is only the case if the input number is 0 or 4, 8. Then I need to find 8 and 12, which is this. And all the other ones are 0. So I was a bit fast in that part because it's like a simple task. But if you have any questions, we can go through that section. Otherwise, I will go through the other sections. Okay. So now, based on this truth table that we prepared, the question asks you to prepare or simplify 2 things. The first one is the D4. First, we should write it in the sum of products representation, which is A naught, B naught, C naught, and D naught, which is the first one from here. And then the second one is A naught, B, C naught, D naught. And third one is A, B naught, C naught, D naught, and then the last one is A, B, C naught, and D naught. So this is the sum of all the products that this output is 1, and we are asked to simplify this thing. And the way we simplify is we're going to merge the terms that have most entries common but differ by 1. And in this one, if we get in the parentheses of A naught, C naught, and D naught, we will see that this is equal to B naught and B naught or B. And then the other one is if we get into parentheses of A, C naught, and D naught, this is also B naught or B. We need to do the simplification in this way first. So we need to first realize that B or B naught is 1 because either one of them has to be 1. And if you have at least 1, 1, the resulting solution is going to be 1. So these are done. And then the D4 is simplified to A naught, C naught, D naught, or A, C naught, D naught. And we can get this into C naught, D naught parentheses by ORing A naught and A. And in the same logic, this is also 1, A or A naught, because either one of them has to be 1. And then the result is C naught or D naught for this solution. Sorry, C naught and D naught for this solution. If you have no, okay. I mean, if you cannot find a simplified solution, and if you are not sure that, for example, what you find is the most simplest one, you can use the Carnot maps. But I think for this solution, it's very straightforward. Once you come to C naught, D naught, it's very obvious that you cannot simplify it further. So Carnot maps will be a waste of time. But if you have time in the exam, like if you solve through all the questions and you just want to make sure that you found a simple solution, yes. And also, even if you did not get the really final solution, you will get partial credits. So I would say do not waste your time on Carnot maps unless you solved all the other questions. Okay, anything else? And then last question, which is about the simplest representation of factorial output. But this question is a bit different in the sense that we have to represent the simplest output using only NOR gates. But I think the easiest way is to start with simplifying the factorial expression, and then we can think about how we can kind of map it to NOR gates. And factorial is, if we also start with the sum of products representation, is equal to A naught, B naught, C naught, D naught, or A naught, B naught, C naught, D, or A naught, B naught, C and D naught. In the same way, we can simplify this equation, because if you just check these two expressions, for example, everything is common except D. And if we get this into A naught, B naught, C naught parentheses, is D naught or D, and A naught, B naught, C, D naught from the third term. In the same way, we can see that this is actually 1, because D or D naught, either one of them has to be 1. And then in an OR gate, if you have at least 1, it's S1. And this equation is equal to A naught, B naught, C naught, or A naught, B naught, C and D naught. We can get this into A naught, B naught parentheses, which is C naught and C, D naught. So we have to simplify this part. And if you cannot see how you can simplify this part very easily, and if you have only 2 inputs, for example, you can just come up with a simple truth table for C and D, and kind of see the simplified thing. And if you see from the expression, if the C is 0, the expression is going to be 1 for sure. And if C is 1, D also has to be 0. And if both of them are 1, you get 0. And that's why you only get 0 when both of them are 1. This part is equal to C, D, and not. So it's a NAND gate. Then we can represent this equation like this. So factorial is equal to A naught, B naught, and C, D naught. And now we have a very simple equation, but the thing is, this cannot be represented using only NOR gates as is. So the way you can kind of transform what you have in terms of products ends to NOR gates is by negating it 2 times and using the De Morgan's law. So if you can negate it 2 times, and then it's going to be factorial. So distribute the first naught to the terms. It's going to be A or B or C, D naught. And then there's only also the second naught. And how it works is that you will negate all the input ones. Since we had A and B in the NOT form, we negate it, and then we just get them without the negated one. And then you should convert all the sums to products and products to sums. Now we have almost everything in the NOR gate form. So if we have a NOR gate, we have 3 inputs now. The first one is A, the second one is B, and then the other one is CD. Because if you negate something 2 times, you will get the original thing. But the thing is, CD is not in the NOR gate form. So everything is done. So we need to figure out how to express CD in the NOR gate form. And CD is equal to CD negated twice. We just use the same thing, which is equal to C naught or D naught. So now we can see that this output is actually equal to NOR gate with 2 inputs, C naught and D naught. But C naught and D naught also cannot be, C naught and D naught should be computed with using only NOR gates as well. And there's a simple trick for this. So for any input, if you have the negated version, it's equal to the NORing the input with itself. So basically, if you just OR the C's and get the negated one, it's going to be if you get the NOR, so basically of 2 C's, you get the C naught. And then you will need to do the same thing for D naught. So it's also a NOR of D with like both these basically. And instead of C, you need to have a NOR gate with 2 C's. And instead of D, you need to get a NOR gate of 2 D's. And if you kind of merge everything, you have one A or B or C naught or D naught actually NOR of these two things and everything in a NOR way. And this is how you can represent the factorial output using only NOR gates. I guess that explanation was a bit more confusing than the other ones. Do you have any question? And it's also the solutions are a bit different than the ones in the solution sheet. But I think it's a bit simpler. Yes. Oops, sorry. Maybe I can go over that part again. So which part you couldn't see? Which is CD. Okay. So we have the AB as is, and then we have the CD input to NOR gates. So we have to represent CD using only NOR gates. And this is, we use the same thing of negating it 2 times, and it becomes C naught or D naught, or NOR of C naught and D naught. And the next thing to do is we should represent C naught and D naught using NOR gates. And the simple thing to do this is using a NOR gate with both inputs from the same signal. So if you just have a NOR gate where both inputs is C, you will get the C naught as the output. This is like a simple thing that you should actually consider because it's used a lot, actually. And it's the same thing for NAND gates as well. So if you have to represent a circuit with only NAND gates, you can negate it in the same way. And this is the final final result that you should give. Actually, you don't have to draw the NOR gates to find the solution, but it's just like easier for you to visualize. But yeah, any other question? Okay. Then for the second question, Joel will come, I guess.
Thanks. All right. I had the fortune of getting the FSM question. So it's a simple one. So the finite state machine question, yeah, should be easy points, but the caveat is that it will be graded quite strictly, probably. So it's easy to get it right, but it's also easy to lose points unnecessarily. So read super carefully, and then you should be golden. So in this one, you're supposed to assign some controller for the polygon, which broke down. So it has 2 doors, which will be outputs, A and B. You can see the exercise starts with a specification, quite precise specification, hopefully. And when you go through this, I guess I want to read it out for you, but when you go through it, basically try to look out specifically for any kind of pointer that might indicate states already. In this case, we already gave you the states that you will be needing. But yeah, in this year's exam, you might not be given the states, I'm not sure. So what you should look for is kind of anything that could be a state, right? So here, okay, we were so nice and highlighted them in bold for you. So there should be idle states, and then unload and emergency and transit states as well. And another important piece of the puzzle, if you will, is that you can see there's multiple places where we're talking about numbers of passengers. So for example, we're saying, okay, the polygon is full when it has 2 passengers. And when it's again full and idle, so somehow the control depends also on the number of passengers, then it will do X, Y, and Z. And then it will unload all passengers. So somehow the passenger count drop to 0. and then the last passenger, so once you're at 0, has exited, it becomes idle again. And then finally, there's an additional specification. It's when it becomes overfull, which is more than 2 passengers. Then it will go into emergency mode. So based on that, I think there's the key takeaway that we should be doing some kind of counter, right? So we should count the number of passengers we're getting. And looking at the inputs we get, fortunately, there are indeed inputs for the number of passengers that enter. So we get 0, 1 when a passenger leaves. So second bit kind of stands for someone left. We get 1, 0 when someone entered. So these are the 2 main inputs, I guess. And then there's 2 special case inputs, namely nothing happening, which you mostly can just ignore. And then 1, 1 is a special case where the polygon has arrived at a station without anyone entering or leaving. Okay, so let's draw the FSM. You're asked in sub-question A to draw a more type FSM. So again, it's one of the places where you should be extra careful in reading, right? Check if it's more type or mealy type. So more type FSM means there are some hints in that exercise, I guess in case you forgot, but the outputs are basically given at the states, right? Not at the edges. So somehow you should parse what's given in the question and fill out the according door outputs A and B. So what did we say? I believe first bit A holds the door open when it's 1. Okay, so let's start in idle state. The passengers can enter through door A. So certainly A should be open, that's a 1, and B should be closed. I believe, okay, if you didn't infer it from this that B should be closed, we have also this statement down here. After the last passenger has exited, door B closes. So it's certainly uniquely determined that this has to be 0. Then while still idle, it remains that door A should be open, B should be closed. Then once we go into transit, let's see. Did we specify it explicitly? I hope so. Right, when it's full and idle, a polygon goes into transit. The other station will with both doors closed. So it's both 0, 0. Then, okay, you can imagine that unloading will happen through door B. So once the station is reached, it should unload all passengers through door B while door A is still closed. So let's call the unload states 0 and 1 and 0 and 1. Okay, and then the emergency state, let's see here. Okay, it opens all doors, remains there. So it opens all doors. 1, 1, fine. So that's the states already done. It's half the exercise basically. But again, it's really easy to mix things up here, right? If you, I don't know, if you do something really bad and invert 0 and 1, that's a stupid way to lose lots of points. Right, so next easy place to lose points here is to not draw a start arrow. So you can see here in the question A, you're simply asked to draw a complete FSM, right? Which in particular involves drawing the transition edges. Then you should draw the input bits for each edge, and you should specify the output bits for each state. And for the edges in particular, you should have a start, the reset edge. So don't forget that one. I don't mind if you lose points that way, but I assume you would. Right, so we want to start in idle state for sure. Initially, polygon is in idle state. Now we should count. Well, I conveniently labeled the states idle 0 and idle 1, with the intention being, hey, idle 0 means there are currently 0 passengers in the polygon. Idle 1 means there's currently 1 passenger in the polygon. And on the other side, unload 2 means there are currently 2 passengers in the polygon. unload 1 means there's currently 1 passenger there. Clearly, when you're given states like that, you don't necessarily have to use the same interpretation that I or whoever designs the question did when giving you the states. But maybe you can get a hint from it, and maybe you also don't get named states, right? Maybe you don't get states at all. Right, so in this case, assuming idle 0 means 0 passengers currently, let's see what happens on input bit 0, 0. There should be no change, so okay, it would usually be a self loop, right? So something like this. But in the question, we're saying, okay, any input bit for which no outgoing edge is specified is assumed as a self loop. So basically, in most places, you can leave 0, 0 just open, omit it, and it will be assumed a self loop. If we don't write this in the exercise, it's good that you write it if you make that assumption. Right? Never leave edges undefined in an FSM, basically. But you can certainly define them in text. Right, so if nothing happens, we stay there, sure. Then let's see, if we have a passenger enter, we go over there, right? So 1, 0, we have now 1 passenger. We were at 0 passengers, now we have 1 passenger, but we're still idle. Let's see, if we had a passenger leave from 0 passengers, that doesn't make a whole lot of sense. So you still need to have an edge defined, even if the input doesn't make sense, right? But in this case, the master solution just also leaves it open. The idea is, it turns out it's a self loop, right? So if you just don't say anything, so here in the case, let's see, 0, 1, we would say we stay idle. It doesn't matter, as long as you, sure, go ahead. Yeah. You can also do more loops. It should be clear that whatever you do, that somehow there is some edge for every input. And in this case, right, for whatever there is no input, we said would be considered a self loop. Yeah, you can do multiple self loops, whatever you want to do. I guess it gets a bit more tricky in the mealy type FSM. You need to be a bit careful with the output bit so you don't confuse input and output bits. Yeah, all right. So basically, it's fine to essentially ignore states that don't make sense or edges that don't make sense, but you should define them in some way. And okay, let's continue here. So if the polygon was idle and it arrives at the station, that's also kind of a nonsense edge. So let's leave that open as well and assume it's a self loop. If you're in idle 1, so we currently have 1 passenger, we could still have a passenger leave, right? So let's see, input 0, 1, exactly 1 passenger left. Then we would go back to being idle and having 0 passengers. Now you could argue that, well, in the question specified, passengers should enter through door A, right? Why did we just have a passenger leave? That should be a nonsense edge as well. But okay, we have this thing down here. So note, passengers sometimes slip through incorrect doors or even through closed doors. Okay, so that sounds ominous, but the entire point behind that statement is that it really, you shouldn't rely on the state of the doors for the correctness of your edges. So we could totally have a passenger slip back out through the door they were supposed to enter, and we handled that here. We go back with an edge. Right. So if we have 1 passenger and they are in idle state, if you get an additional passenger, we should go into transit. As specified, where when it's full and idle, the polygon goes into transit to the other station with both doors closed. So full is at least 2 passengers. We had 1 passenger, we added 1 more. Now we go into transit right away. That's fine. Now during transit, what happens? Well, if you have a passenger entering or leaving, so if you have a passenger leave during transit, I guess they fell out, as specified here. If you have a passenger fall out during transit, so it should go into emergency mode. Sure, let's try to avoid losing passengers along the way, but if we do, we go into emergency. And then we have also the option if the polygon becomes over full at any point, so at least 3 passengers, then it should also go into emergency mode. Now, the only 2 times we really have at least 2 passengers is in transit and in unloading. So if during transit somehow there's a passenger hopping on unexpectedly and the polygon is too heavy now, it's over full, then we should also go to emergency as specified here. Right, and then in emergency, we just remain there. As you can see, there's no outgoing edge, essentially. It remains there unless we set to idle state. So you could again draw this with kind of, a self loop and specify everything, or you might as well specify nothing and just rely on the fact that specifying nothing means a self loop, as we said here. All right. Then from transit, assuming we didn't get anything unexpected happening, we should eventually arrive at the station. So we should get the signal 1-1, poly1 arrived at the station. And then we would be in state unload 2. Because we had 2 passengers on board, we're now unloading 2 passengers and there are still 2 left to unload. If we're currently in unload 2 and there's an additional passenger entering, and we get the same issue again, the poly1 becomes overfull and we should go to emergency mode. That's fine. Now, hopefully, instead of entering during unloading, passengers indeed leave, so we can have the edge 0-1, go to unload 1, there's only 1 passenger left. And if we unload another passenger, we go back to idle. Great. If during unload 1, we have another passenger enter again, then we go back to unload 2. We're still trying to unload our passengers, but well, unfortunately we have 2 again. And the other edges we can again leave unhandled, or rather assumed a self loop, because they make no sense to get as an input. Right. Any more questions about this part? Hopefully this looks the same now. So on the master solution, let's see. Yeah, looks about right. Okay. Yes. Sorry. That's right. Yeah. So we specify up here, right? Let's see. Okay, at any point it stops in emergency mode, where it opens all doors and remains unless reset to the initial idle state. That's kind of an external thing resetting. Okay, cool. So, second part of the question. This one should be rather easy points if you solve the first one carefully. So now you're supposed to design a second FSM that's based on the first one. Namely, you should ring a bell. So what that means is your output bit should be 1 whenever the earlier Moore type FSM opens or closes a door. Right? And it's constantly ringing in the case of an emergency. So, and by the way, it also says you're supposed to do this as a melee type FSM. Right. Now, melee type, recall melee type means there's no more outputs at the states. So in Moore type FSM, there were these output bits right of the state, or even placeholders for it. Here there are no placeholders because the output bits in a melee type FSM is supposed to be on the edge. So you're supposed to kind of take the same FSM, right? You need to keep track of the same states. Somehow, every time you're in a state here, you're supposed to be in the same state over here. So you need to keep the same control logic, if you will, but your outputs need to be different because, well, you need to have a bit 1 whenever your doors here change. So what you can do essentially is just copy all the edges for now, at least the edges input bits. So 0, 0, 1, 1, 0, 1, 1, 0, 1. Are you missing any? Yes, we are. Okay, I think now we should be good. Don't forget the reset state again. Okay. I omitted now the unnecessary self loops again. What's important to note here is that, first of all, we have to give an output bit for each of these edges. And the self loops now, right? Since we're just making an assumption what a self loop is supposed to mean if it's undefined, we're saying, okay, if you leave something unspecified, it's a self loop with output bit 0. So if we need anything else in a self loop, we have to explicitly specify that self loop. So let's see what our output is supposed to be. So the bell should ring whenever the more type FSM part A opens or closes the door. Well, between idle states, it certainly doesn't change anything. So if you just remain idle but with different passenger counts, there should be no bells ringing, no doors open or close. We close from idle state to transit. We of course close the door, right? We start driving. So the output bit is 1. Then when going into emergency state from transit, we open all doors. So certainly both of these should be an output bit 1. If you go for transit into unloading, you should have a 1 because we open the unloading door B. And then between unload states again, nothing changes. So no bell ringing. And between unload and idle, we do have a bell ringing because we close door B and we open door A. Right. Now there's one more edge missing here. And that's what I pointed out before. Any self loops are assumed output 0 if they're not specified. So when we read the specification of the emergency state, it says the bell is constantly ringing in case of emergency. So when we are in emergency state on any input, so let's say input XX, you could also specify all 4 inputs, if you will. But if you put XX or star star as a placeholder, that's fine. Then it should also be ringing. Okay. Yeah. You're right. Thanks. See, that's how easy to lose points. And I even put colors there. Thanks. Right. Yes. It should be 1 because we open door A, I guess. Okay. Now hopefully you have an output at every edge. Yes. Any questions? All right. Then we can go on to the next one, I guess. Thanks. Who's next, Mohammed?
Am I audible? This is a relatively very simple question. ISA vs microarchitecture, circle whether each of the following is an aspect of the ISA or the microarchitecture. So generally, ISA refers to the interface between the underlying hardware and what the software sees or what the programmer has access to. And microarchitecture is how underlying hardware is actually implemented and is working. In the example, please also pay attention to this note. I read over it very quickly now. We will subtract 1 point for each incorrect answer and award 0 points for unanswered questions. Okay, let's get to the first item, two-level global branch predictor. So as a programmer, like in general, software does not need to know about that. So that's how things are implemented. Location of the bits that identify the destination register in an add instruction. So that is what we actually need to know if we want to write a program. Number of the instructions fetched per cycle, again, microarchitecture. Ratio of the number of floating point to integer general purpose registers. So here, the ratio is not like very important, but we know the number of registers. So we need to know how many registers we have to work with, both floating point and integers. So subsequently, we can also have calculate the ratio of them. So let's see ISA. Number of integer, arithmetic, and logic units or ALUs. Again, we don't need to know about it. It's just how things are implemented. Instruction issue width of the processor core pipeline. It's again microarchitecture. By the way, if the reasoning behind any of these choices is not clear, please stop me. Nice, okay. So SIMD supports ISA because then we need to know whether we can use it or whether we can use it in our software code. L3 cache replacement policy, again, microarchitecture. Width of the data bus to memory. Microarchitecture, we don't necessarily need to know the width of it from outside. The size of the addressable memory by the programs, so that is clearly ISA. The number of cycles it takes to execute an add instruction, microarchitecture. Ability to choose a specific cache replacement policy using operating system core, that is ISA. So if the system had already a replacement policy which we couldn't choose, then that would be microarchitecture because that's how the underlying thing works. But here it's referring to a scenario where we can, from the software side, select which replacement policy to use in our hardware. So that's why we choose ISA here. Number of read-write ports in the physical register file. So that is microarchitecture. Function of each bit in a programmable prefetchers configuration registers. So that is again something programmable. The user can change it. ISA, number of L3 cache banks. That goes into microarchitecture because that refers to how things are implemented actually. So are all these choices clear to you? Okay, then. I think we're done. Maybe. Oh.
Hello, everyone. So we're going to solve the fourth question of the last semester, final exam, which is Verilog. So the first one, yeah, it's like this. So the first question asks, what does this code do? Analyze the following Verilog module and answer the question. Let's first take a look at the module. This module is called mystery module. It has four inputs, clock n, in1, in2, and one output, which is in reg, which is out, and one register variable, which is vr1. So here we have always post block. Here we have two main if clauses. And then this is the always block. So let's take a look at the remaining part. Assume that the inputs in 1 and in 2 always have the following values. In 1 is 64-bit. In hexadecimal base, it's total of, I guess, 16 digits. So here, please note that every digit is 4 bits. So here in 2 is 8 bits length, and it has 8 bits, which is 8 digits. So it asks what unsigned decimal values does the out signal get in the following waveform diagram. So we need to fill this all 11 gray boxes. So let's start. So for the first one, we know that, so this is postage clock, right? And this is the always block. What happens is in that when we, let's say, start executing this block, the variables that are assigned in this block updated at the end of the cycle, which means that this postage clock 0 will be executed here, but the results updated after this cycle. So here we know that the initial value is 0, right? So the out becomes 0. So here, this out will be updated using this one. So here we see that enable is 0, right? So we go to this if clause, enable is 0. We cannot satisfy this one, and variable is 1 is initially 1 here. So that makes output is again have the same value as the previous one, which is again 0. So this postage clock 1 will affect this one. So here we see that there's a, let's say, enable has increased, risen. That means that enable becomes 1. Now that means that this if clause, which is in the 12th line, will be satisfied. But that means as variable 1 becomes 1. But it becomes 1 after the always block executed. So now it's still 0. So here we go to this if block into variable 1 with what that means is into 0th bit. We check this 0th bit, it is 1. We also satisfy this one. And then out will become 0 plus this. So I know you're not familiar with this one. This means that this is the base. And this is how many bits you'll count afterwards. So let's do that with example. So we know that variable 1 is still 1 here. So what that means is, maybe I can write here, in 1, 0 plus 8, which is equal to in 1, 7 to 0. So you start from this space, you count 8 bits. So we take a look at here. So we know that each digit is 4 bits. So we take 0, 1 out from here. So what that means is 0 plus 1, output will become 1 after executing this. So means that here is 1. So when we execute this one, so 1 is 1 now, we are 1, and out is 1. So let's execute that one again. So enable is now, it doesn't matter, variable 1 is 1. So we don't go into that loop, that block. And we check this if, 21st one. So variable 1 is not 1. Now we go into that one. So variable 1 becomes 2 here. But it will be updated after this always block executed. So here, line 24, we'll check into first bit, not the second bit, but the first bit. First bit is 1. So which means that we will go into this clause. So out will become out plus in one variable 1 multiply 8 plus 8, which that means in 1, 8 plus here we will do like out is 1, in 1 is 2. Now out become 3. So now we will execute the third one, fetch third. So here we is out, which is 3, which was 3. And this one is, we know that we already know, this is also 3. This is 8 bits. So 3 minus 3 is 0. Now out becomes 0. So now we will continue doing that again and again. So here again, variable 1 was 4. Now we get the 4. 4 is 1. And that means that we will perform addition. Out was 0. And corresponding in 1 is 4, which makes out 4. And then we execute again the fifth one. The in2 is 1 again. And what that means is out will be updated as 4 plus 5 here, which is equal to 9. And then we will execute again. So again, it's, I guess, yeah, 1 here. And then we will go into this clause. We will increase the var 1 and we'll check this if, which is 1. And we will perform addition again. Out was 9. In 1 is now this part is 6, which makes 15. And then, so we increase the var 1 and make the out 15. Now in the next cycle, we execute again the always block where 1 is now, I guess, 6, yes, and which is 0 in the in2. So which means that we need to perform subtraction here. It was 15 and this one is 7, makes it 8, I guess. Yes. Okay. Now we perform the same thing again. Now where 1 is 7. 7th bit of in2 is 1, means that we need to. So here, sorry. So where 1 was 7, right? So we increment where 1 by 1, which makes it 8. But the problem here is where 1 is 3 bits. So 8 is actually 4 bits, right? 1, 0, 0, 0. What happens is that where 1 takes the least significant 3 bits, means that you reset the where 1 to 0. So in the next cycle, where 1 becomes 0 again. So, but let's execute this cycle. So where 1 becomes 0 here, we check 7th bit of in2, which is 1. And then we perform addition, 8 plus 8, which is 16. Now, in the last cycle, we know that where 1 is 0. And you see that enable is also 0. What happens here is that enable is 0. We don't go into that block. And where 1 is also 0. Don't execute that block. It's the same as the first cycle. So output will get the values as the same as the last cycle, which is 16. So that's the first question. Do you have any questions on that one? Yes. Mm-hmm. Yes. Yeah, so you need to keep track of that. It's a little bit tricky. Yeah, but you see there's a pattern over there. You increase by 1, you get 8 bits of chunks. And yeah. So the second question, let me check. This one is relatively easier than the other one. Let's see. So here it says that there are numbered blanks 1 to 5 in the following Verilog code, and we have to choose one of the options over here. So let's start with the first one. So the model called my model, input clock, input reset, input data, and we don't know the type of the result. So when we checked the choices, output track 0 to 0, and input track. So we can understand that there is no such thing as input track. It's a syntax error. We can eliminate that easily from just looking at the second line. So when we check the line 24, we see that they used assign. So if it was rec, we couldn't use assign here because rec can be only, let's say, updated inside the always loop, always block, and we cannot use assign keyword for this one. We should use, let's like this state. So which means that result is var, and we won't use rec over here and here. So which makes A is the correct option. So for the second one, it's state, and it asked, I think it asked the type of the state. It says defining a 2-bit signal with an initial value of 0. So you can understand that it says initial, so which means that it will change in the cycles, and we use state inside of the always block, right? So which makes it rec type. So we will use rec here. So it says that defining 2-bit. So that's why we cannot choose B. So the only option is A. So for the third one, it's line 9, I guess, and it says a set the next state to 2-bit 1-1, which is 3. So we check the A, 1-bit 3. It's not possible. It's not a correct syntax because so this indicates the base, right? In the binary base, we only have either 0 or 1. So you cannot say 1-bit 3 over there. If you want to use 3, you can use hexadecimal or decimal base. So it's not syntax correct, this one. And B is also the same. If it's a binary base, you can only use 1 or 0. So in the C, we see that it's a decimal base, it's 11. Yeah, we can say that. But it's 2-bit length. But our variable is 11 is 4-bit length, right? So again, it's not correct. So D is the correct one, which is 3. When you don't say anything, explicitly say anything like the bit length and the base, it's directly says it's a decimal base. So you can easily use this one, which means like decimal base 3. So the correct answer is D. So for the fourth one, it says line 15, set the next state to 2 bits 0, 1 if all bits of data are 1. So what that means, it's beginning of the, let's say, variable here. So we can understand that this should be like reduction type of thing. So that's why we will eliminate A here. And D, it doesn't make any sense. One data is like, again, error. So only choice are B and C. So we know that it says that if all bits of data are 1. So which means that we have to perform AND reduction, and then we will understand that if the all bits are 1, right? If we use, let's say, C, it's a logical negation. So we have 8-bit of data. It will get the least significant bit, and that's why you won't satisfy this, let's say, constraint. So the correct answer is B. So the last one is 5th. It's in the, again, line 24. It says that assign 1 to result if the state has any bit set to 1, otherwise assign bit 0. So we know that it's, again, a similar situation, right? So it's in the beginning of the, let's say, the variable. So we cannot use C over there. So we know, it's also said that it has any bit set to 1. So it should be all right, or if any of the input is 1, the result is 1. So it's easily we can easily say that it's OR reduction, which makes it A. Do you have any questions on that one? Okay, thanks.
Hello. So this is another true false question. before I start with the questions, the policy for these sorts of questions we have is basically if you circle the incorrect answer, we deduct 1 point. If you do not circle any of the answers, if you leave it blank, you don't get any points. And if you do it correctly, you get for this question, you get 2 points each question, each true-false question. Okay, so I'll start with the first one. So I already have the answers circled here. So I'll start with the first one. I'll try to explain the reasoning behind the answers. The first one is a main memory access typically consumes less energy than a register file access. And this is false because typically it's the other way around, right? We have our register files inside the CPU. It's very close to where we do compute. So it's a small structure compared to main memory. So it takes much less energy to access it than main memory. The second is building a larger memory array by increasing the length of the array's word lines and bit lines increases the cost, but does not increase the access time of the array. So the first clause is correct, it increases the cost. But the second part is incorrect because increasing the length of the array's word lines and bit lines will increase the access time because we have longer wires to drive. Yes. Yes. I think you can do that, yes. It's a good abstraction, yes. Okay. The third one is activating a DRAM cell temporarily destroys the value stored in the DRAM cell. So this is true because if you remember from the lectures, main memory lectures, when we activate a DRAM cell, we're activating a word line that connects the cell to the bit line. And after the bit line, after the cell is connected to the bit line, it will share its charge with the bit line, meaning that whatever value it was holding on to is now essentially gone because it shared the charge with the bit line. The charge level in the cell is no longer as it was before we accessed it. But what happens is if you wait for a little longer, the sense amplifiers will be enabled and then write the value back to the cell. So temporarily the value is destroyed, but it will be written back. And that's why this is true. The fourth one is DRAM cost in dollars or Swiss francs per bit is much higher than that of SRAM. This is false because, I mean, the real reason is really manufacturing technology limitations, but another way to find this out is basically we don't have SRAM that is as dense as DRAM in our systems today, and the main reason is essentially cost. Okay. Yeah, DRAM costs much less to produce per bit than SRAM. The fifth one is the memory hierarchy of a typical computer system comprises different memory technologies. Again, if you think about the two most common things we have in the memory hierarchy, the caches are built usually using SRAM, and the main memory is usually built using DRAM. So that's why it's true. And if you look at storage, that's even a different technology. Like SSDs, we have flash. Yeah. Recently accessed data should be kept at the bottom level in the memory hierarchy, bottom level meaning the main memory or disk, but not at the top level, meaning caches. And this is false because if you're frequently accessing a data, you want to keep it close to your processor. So you want to keep it at top level because you can access it much faster. So putting it in main memory or disk does not make much sense because you spend more energy and more time to access that data. A program with no branches has high temporal locality in its instruction memory references. So a program with no branches will have instruction memory references like these, right? So these are byte addresses. This is just an example. And imagine we put our program starting from the 0th address in main memory, and each instruction is 4 bytes. we'll have an instruction memory reference stream like this when we execute this program. It will go on forever, and there's no way for this program to access a byte that it accessed before in terms of instruction memory reference, because there are no branches in this program. So we'll just move on. This means none of the instructions this program brings, it uses twice. That's why there's no temporal locality being exploited here. Is this clear? Okay. And then the next one is a cache that has a block size equal to the word size of memory access instructions. Okay, it's not visible now. Oh. Yeah. Cannot exploit special locality. Yes, so let's look at what we have today typically. So you have this cache line size, let's say, of 512 bits, right? And let's say your word size is 32 bits. This means you can fit 16 of those words in this cache line. Why this is important is you will access this word from your processor. The processor executes a load instruction to this word that I highlight here. But we will end up bringing all these other words in the cache line to the cache. And if there is special locality in the access pattern of the processor memory requests, it might be the case that we will, for example, next access this word. And this cache essentially enables us to exploit spatial locality. But the cache we're describing here has a block size equal to the word size of memory access instructions. So when the processor accesses a 32-bit word, it will end up bringing the whole cache line, right? So there are no other words that we can access in that cache line, and there's no special locality to exploit. Okay, this is the reasoning behind this statement being true. Is there any problem with that? No. Cool. The next one is memory banking enables concurrent access to the memory structure. This is correct. If you remember again from the main memory lectures, we can have, in the case of DRAM specifically, we can activate one row in a bank, and immediately after that, we can activate another row in a different bank. Essentially, at that point, we say, okay, we can access these banks concurrently, right? We overlap the latencies of many different operations. Okay, 10 is in DRAM, accesses to different rows in one bank can be serviced faster compared to accesses to the same row in one bank. This is false. So the first clause is describing, so this part, different rows in one bank. This is describing a row conflict. That means you have a row enabled. Basically, this access pattern will have a lot of row conflicts or bank conflicts. This means that you enable a row, you spend some time to satisfy the latencies, the timing parameters, and then you pre-charge that row, you enable another row, you pre-charge it, enable another. It's like a double-sided RowHammer attack, if you remember that. So basically, to service the next request, the memory controller has to close a row, open another row. Closing and opening rows takes long time. Let's say it takes, this takes TRC amount of time. This second part describes access to the same rows, same row in one bank. This is a row hit. And then we only have to wait for, the memory controller has to only wait for a very smaller latency. This is like TCCD, which is TRC, you can think of it as around like in the order of 45 nanoseconds, and TCCD is much smaller, like, I don't know, smaller than 2 nanoseconds. Basically row conflict, and we're questioning row conflict and row hit latencies here, yeah. Not exactly like that. It's just that when you have a row already enabled and you want to access another row, you have to first pre-charge the bank, like close the open row, and then activate the next row, like the actual row you want to access. And you have to wait a very long time to do those operations. But if you're accessing a row that you have enabled, that means you're servicing that access from the row buffer. So it's already enabled. You have the data ready to be pushed through the I/O, essentially, out of DRAM. That's why it's much faster. Okay. So 11 is PCM is non-volatile, which means PCM retains stored data even when it's powered off. And this is correct because that's how PCM works, I guess. This is some sort of, you know what non-volatility means, and then you just decide that this is correct. Okay. 12 is if a hypothetical system is not constrained by chip area, memory cost, energy consumption, DRAM would be the best memory technology to use in that system. This is false because when you're not constrained by these three things, essentially you want to improve, like you're looking for the best performing memory technology, right? That would be not DRAM. One example is SRAM. You can have SRAM arrays at the providing the same density as your DRAM chip because we don't care about cost or area or energy consumption. We choose the fastest memory technology. That wouldn't be DRAM. That's why this is false. 13 says the entire page table is typically stored in physical memory. This is false. And the reason for that is if you think about the page table for a program, because you have to have many mappings from all possible virtual addresses to the physical addresses. We have these multi-level page tables, which enables us to essentially have some of the possible mappings not in physical memory. So this has something to do with the multi-level page tables. If this is not clear, I can come back to it. But otherwise, I'll move on for now. And you can, at the end, let me know. So 14 is virtual to physical address translation is on the critical path of a memory access. This is correct. You have to, your program uses virtual addresses. You have to translate that virtual address to the physical address to access main memory. That's why it's on the critical path of a memory access. And finally, virtual memory makes programmers and microarchitects tasks easier. This is false. The first part is correct, right? Virtual memory makes programmers tasks easier because the programmer at least does not have to care much about memory allocation. They still need to care about it, but not as much if you don't have virtual addresses. But microarchitects' tasks are not necessarily easier, right? Because they now have to implement these new structures that translate from virtual addresses to physical addresses and potentially improve on them. That's why this is false. And that's the end of question 5. Yes. I think here we're basically the entire page table is typically stored in memory. What's the other alternative? And then you think about disk, right? But it's not stored at all. Is a better way to think about this question, I think. Basically, you don't need to, in the multi-level page table, you don't need to have some levels initialized at all, right? You put enough mappings into your physical memory such that basically you put only the necessary mappings there. Yeah. Okay. Cool.
Okay, can you hear me? I guess so. So this is the classic performance evaluation question. So in the introduction, it tells you that you are working on a project called Awesome Memory, where your goal is to optimize the memory hierarchy for a particular multi-core architecture. And basically, you are evaluating two different systems. One system that is the baseline system, and the other system that is this Awesome Mem system. And then to evaluate these two architectures, you run some tests, and the tests are described here in this 1, 2, 3. So first you collect some performance metrics for single thread applications at 1 to 4. They run in isolation in the baseline. So they run by themselves, each one of in a core. Then you create two application mixes to perform a multi-program simulation. So you have two cores. Basically, you're going to run one application in one core and another application in the other core. And they are going to run concurrently, both in the baseline and in the also mem configuration. And we are going to evaluate those two application mixes. Mix 1 has application 1 and 2, and mix 2 has applications 3 and 4. So you run all of those tests, and you collect the data that is in this table here. So if you look at the table, we have the execution mode, the single-threaded multi-programmed. The application mix is only relevant for the multi-program case. The configuration, both the baseline and the also mem, the applications, and some metrics. So here you have executed instructions, executed cycles, last level cache miss rate, branch misprediction, and DRAM bank conflicts. And then it's going to ask you to do a bunch of small questions on top of it. So the first question is asking you to calculate what is the instruction per cycle, IPC, of each one of those 4 applications when running in isolation in the baseline configuration. So IPC, as is written here actually, is the number of instructions divided by the number of cycles of a particular application. And so basically you need to check the table and fill up the instruction in the cycle. So for application 1, the number of instructions executed is 100,000. And the cycles is 40,000. You don't need to do the math on this particular part of the exam. If you just leave it like this, like 100,000 divided by 400,000, I'm going to grade you, I'm going to give you 100% of the exam. If you try to do the math and don't write down the equation and write down the wrong value, I'm going to cut your points because I don't know which math you did actually. And if you do math and I cannot follow all of the steps, like there is beginning of the end, there is a high chance of me reducing some of the points because I don't know exactly how you went from A to B. So the best thing to do in a performance evaluation question is just leave it like this and you're safe. So then you continue doing this for all of the applications. IPC of application 2 is going to be, again, all of them are 100,000 actually. And just there's the number of cycles is going to change. Is 800,000 for app2 is here. And then 500,000 and 20,000. Okay, this is good. Any question here? Okay, it's quite straightforward. And then here is telling you, probably you are not familiar with this metric, but we are giving the definition. So in the end becomes again a math problem. So to ensure that the system throughput of a core system to measure, the student uses the weighted speed up metric, which sums the instruction per cycle, IPC that you just calculated, slow down, experienced by each application compared with when the application is running alone. So when you run 2 applications in a system that has shared resources, this application can experience a slowdown because, for example, if they want to access the L3 cache or the DRAM, they are going to have to compete for those resources. So this metric is basically measuring that slowdown that you are on top of the multi-threading or multi-parallelism that you are inputting to the application. So basically, the way to calculate system throughput or weighted speed up for workload mix is the sum of the applications running in that workload mix, where the denominator here is the IPC of that application when it's running in a shared environment, divided by the IPC of the application when it's running alone. So this might be confusing if you're not familiar, but we're going to break down the calculation in 2 steps. So it's going to be more or less fine. So first here is asking you to calculate the IPC shared for application 1, 2, and 3, and 4 of the 4 applications when they are executed concurrently in the multi-program application mix for baseline and awesome configuration. So the calculation is the same. IPC is still instructions divided by cycles. But then you're going to consult another part of the table. So here you have the table, you have the multi-program workloads. For the mix 1, you have application 1 and application 2, and is asking for the baseline. So you're going to get the instructions for this row here is again 100,000 divided by the number of cycles, which is 200,000. And this is the value for the IPC shared according to the table for application 1. And then this is asking to do the same thing for the configuration of also mem. So you look again here in this table, multi-program, mix 1, also mem, application 1. The instructions now change to 80,000. And the number of cycles is 100,000. Again, you can leave the math like that. You don't need to solve the math. So you do the same for application 2. Again, you go to the table. Application 2 is here. For the baseline, number of instructions, again, 100,000. Number of cycles is 900,000. And then again, for also mem for application 2, is this row here. Number of instructions is 80,000. And number of cycles is 400,000. Just notice that these numbers are really small. I need to make it larger next time. And then you continue doing that for application 3 and application 4. I'm going to look at the solutions actually because I'm going to save us some time. But is basically 100,000 divided by 60,000 here. Here is 80,000 divided by 400. And this is 100,000 divided by 20,000 and 100,000 divided by 20,000 again. Is there any question here how this was calculated? Basically, I probe the row. Maybe I show the solution here. That is more beautiful than my handwriting. Any questions? Okay, I'm going to give a minute for you guys to copy. Yeah, don't worry about those small values here. Don't expect you to calculate them. So then it asks you to calculate the weighted speed up for each one of the 2 applications mixes when running the baseline configuration. So if you look at the equation here, let me remove this. So weighted speed up is you need to divide the IPC when running in a shared environment divided by the IPC when running alone. So this is going to be for mix 1 have application 1 and application 2. So the weighted speed up is going to be the IPC shared for the baseline, right? Of application 1 divided by the IPC alone of application 1 plus the IPC shared of application 2 divided by the IPC alone of application 2. And you already calculated all of those in the previous 2 questions, actually. So you can just copy and paste the values over here. So one thing that a lot of people got it wrong, maybe it was not a lot, but was not 1 or 2 people in this question, and was not necessarily a problem with understanding the numbers. So the sum of A divided by B is different than A1 plus AJ, let's say, so those 2 things here are different. So a lot of people last time was actually summing the IPC shares of app1 and app2 and dividing by the IPC alone of summed of the IPC alone of application 1 and application 2. That is mathematically wrong. So the sum is you need to do any fraction, a fraction first, sum with another fraction. So I think this is what people were getting wrong last year, actually. So here you just collect the values that you calculated in the previous questions. So here should be, I'm going to put here I have the fraction numbers already, so I'm going to put them here. 0.5 divided by 2.5 plus 0.11 divided by 0.125. Again, I don't expect you to, we don't need to write like this. You can just write the fraction. If you just write here, for example, I think that should be, is this correct? Is here actually. So which value is the one that calculated here? If you just do 100,000 divided by 2,000 divided by the IPC alone of application 1 is this one, 100,000. I'm getting from here. Divided by 400,000 plus for application 2 is 80,000 divided by the 100,000 divide by this other value here. That is good enough to get the points. So just plug and play the numbers, and that's good. Is there any question here? So basically, and then in the next one, it's going to ask you to do the same thing for mix 2. So mix 2 has application 3 and application 4. So this is going to be IPC shared app3 divided by IPC shared, oh, sorry, alone app3 plus IPC shared app4 divided by IPC alone app4. And if you look at the previous exercise that we did in question A and B, this should be 0.16 divided by 0.2 plus 5 divided by 5. Okay, so this question D was also some question that people got something wrong last year. So now it's asking you to calculate that weighted speed up when the application mixes are running in the RowHammer configuration. So you do the same thing. So weighted speed up, IPC shared app1, mix 1 is app1 and app2. Divide by the APC alone of app. 1 plus IPC shared app2 IPC alone of app2. So if you look at the previous questions, we already calculate the IPC shared, right, of app1, app1 and app2 in the awesome configuration, right? So you have them here. But we don't have the IPC alone of app2 running on the awesome configuration. And if you look at the table, the information is not given as well, because actually you don't need that information when you're calculating your alone baseline system is your baseline configuration that you run the applications. You don't need to run them again in the awesome. So the IPC alone is when you're running the that application in the baseline system alone. This is why it's called baseline, right? And so a lot of people got, I guess, confused with this and they said, oh, I cannot calculate this, but actually you can. It's just use IPC alone of the baseline because it's the single threaded system. So I'm going to do this one just because it might be confusing. So the IPC shared of app1 that we calculated before, also is 80,000 divided by the 100,000. And for app2 is 80,000 divided by 400,000. And the shared IPC, the IPC alone of app1 and app2 is of the baseline that we calculated in the first question. So it's 100,000, 400, and 100,000 divided by 80,000. And this is the answer. Again, I'm going to highlight that this is really important. You cannot sum the numerator, the numerator and the denominator when you have a summation. And I would give you that I would grade you wrong because not grade you wrong. I would cut your points because everyone should know this. And then the same thing for mix 2, and in mix 2 is app3 plus app4. So this is IPC shared of app3 divided by IPC alone of app3 plus IPC shared app4 plus IPC alone app4. And I'm going to look at the solution because I don't want to copy the whole values. This is 0.2 divided by 0.2 plus 5 divided by 5. Okay, is there any question here? Okay, great, it's quite straightforward. And then there is a more qualitative question here. So it's asking that the student do not want to review the primary technique behind this awesome configuration. When asked, they provide a list of architecture techniques and told you that some of them could be the reason behind awesome system throughput improvements, awesome memory systems throughput improvement. And so the first one is that awesome memory increases the last level cache capacity by 2 times that of the baseline. Also randomizes memory requests to reduces DRAM bank conflicts. Also employs a perfect branch predictor that always predicts a branch direction correctly. And also employs a efficient hardware prefetcher. And it's asking you which one of the above cannot be a possible reason for also higher performance over the baseline, and explain your reason based on table 1. So basically you need to look if one of those metrics here are being affected by one of those things that are saying here. So the first thing is that also memory increases the last level cache capacity by 2 times of the baseline. So look at the table here, last level cache capacity. You're going to look at you're going to compare also mem and the baseline for a single application, right? So if you look at the miss rate for the last level cache for the mix 1 versus in the baseline versus in the also mem, you can see a reduction, right? It's not necessarily a 2 times reduction, but it's definitely a reduction in the number of less level cache misses. So, and usually when you apply a technique in computer architecture, usually you don't see necessarily a linear impact of like, oh, you reduce the number of, they improve the cache size of 2 times. It does not mean that you're going to see a decrease in less level cache misses of 2 times, but you should see a decrease if your application have some degree of excess going through the less level cache. So just that indicates that, okay, this might be true. That is possible. Also, memory randomizes memory request to reduces the word here, DRAM bank conflicts. Again, you look here, there is a column DRAM bank conflicts, and you can see there is a reduction in the DRAM bank conflicts when you go from the baseline and the also mem configuration. So, okay, this might be true as well. So the answer is the 3, but I'm going to go to 4. Also, mem employs an efficient hardware prefetcher. So what does a hardware prefetcher does? It brings data, right, from main memory to the cache to try to avoid avoiding you to miss on the cache, right? So your goal is to increase the hits, the number of hits that you have in the cache. So again, you can see there is a decrease in the number of misses that you have in the cache. So because of that, you're going to see increasing hits, right? As a ratio. So this also might be true. So it can also be possible that this is a possibility. The third one also employs a perfect branch predictor that always predicts a branch direction correctly. So there is a column here that have a branch misprediction, and you can see for all of the configurations always 1%. So it might be the case that your baseline branch prediction is already so good, and you don't, even if you improve it, you don't see improvement. Or might be the case that you don't see an improvement because this is not the technique. And then there is a keyword here, actually, perfect. If it's a perfect branch predictor, you should never mispredict. So this is the answer, 3. So you could argue in all of those things that I said. You could argue that there is no decrease in the branch misprediction. We could argue that this value is not 0 and should be 0. All of those things will be reasonable explanations. And that is pretty much that. Is there any question related to this question? Okay. You're going to have a 6 minutes break right now.
Hello, everyone. Let's continue the solving session. So I'm going to solve the Tomasulo's algorithm question. And as you may have seen throughout the course, out of order execution and Tomasulo's algorithm is one of the most fundamental concepts in modern processors. And I'm sure there will be a related question in the exam, either some sort of out of order execution question or Tomasulo's algorithm question. So let's start with the definitions here. So what do we have? We have an in-order fetch, out-of-order dispatch, and in-order retirement execution engine. It's the same as the ones described in during the course. And it says that it employs Tomasulo's algorithm, right? And we have the following characteristics. 4 pipeline stages: fetch, decode, execute, and write back. It says that the engine can fetch 1 instruction per cycle, decode 1 instruction per cycle, and write back the result of 1 instruction per cycle. The engine has 2 execution units, an adder to execute add instructions and a multiplier to execute mul instructions. The execution units are fully pipelined. The adder has 2 stages, E1 and E2, and the multiplier has 4 stages, E1, E2, E3, E4. And the execution of each stage takes 1 cycle. Please, whenever you read these characteristics, be sure of which are relevant for the question you're solving, because not all of these here are relevant to the question. Some of the characteristics here are not needed for you to solve the question. The next one is important, that's why I'm saying that. It says that the other has a 2-entry reservation station. What does that mean? We can perform 2 additions at the same time. And the multiplier has a 3-entry reservation station. We can store 3 in-flight multiplications. And you can see that in the text here, we have 2 entries here for the addition and 3 entries for the multiplication. So this is a really important detail that you should track down and note when you solve the question in the exam. So the next one is also really important. So this is an important one. An instruction always allocates the first available entry of the reservation stations in top to bottom order of the corresponding execution unit. Top to bottom means that, for example, here, as you can see, the first question, this one is the oldest one, right? Why? Because it's in the bottom. Jim. So full data forwarding is available. During the last cycle of the execute stage, the tags and data are broadcast to the reservation station and the register alias table. What is the register alias table? The register alias table shows us for each register the validity of the register, whether the register depends on some specific computation from the reservation stations, and this is pointed to with the tag. So as you can see in image B, here some registers have some tags. For example, register R5 depends, yes. Oh, sorry, yeah. Now, yeah, sorry, I will fix that. So here, register R5 depends on the tag X. So the tag X is basically the tag that says, okay, whenever we compute the tag X, we will be able to populate again R5 and know its current value. And it says here, for example, an add instruction updates the reservation station entries of the dependent instructions in the E2 stage. So the updated value can be read from the reservation station entry in the next cycle. Therefore, a dependent instruction can potentially begin its execution in the next cycle. This information is not really important given the questions that we will have later. The multiplier and adder have separate output buses, which allow both the adder and the multiplier to update the reservation station and the route in the same cycle. Again, given the questions, this is not really relevant. And an instruction continues to occupy a reservation station until it finishes the write back stage. The reservation station is deallocated after the write back stage. This is important only for a small amount of, let's say, information that are needed in the exercise. So let's go to the problem definition then. So the processor is to fetch and execute 5 instructions. Just note this down. We need to, at the end, you need to report 5 instructions, even though As you can see in the reservation stations, there are 4 tags. There is probably one instruction which was executed before these 4 tags exist in the reservation stations. So as you can see here in the reservation stations, we have Z, X, Y, and T. These are 4 ongoing operations, but we have 5 instructions. So there is at least one basically there is one instruction that was executed before all these in flight because the snapshot was taken only with these 4 in the reservation stations. Okay. Assume the reservation stations are all initially empty and the initial stage of the register alias table is given below in figure A. Instructions are fetched, decoded, and executing as discussed in the class. At some point during the execution of the 5 instructions, a snapshot of the state of the reservation stations and the register alias table is taken. Figures B and C show the state of the RS and the RAT at the snapshot time, and it does indicate that the value has been cleared. A question mark indicates that the value is unknown to you. A question mark doesn't mean that there's no value. It means that you just don't know it and you don't care about it, right? Don't confuse yourself with that. So let's see the questions. Based on the information provided above, identify the instructions and provide the data flow graph below for the instructions that have been fetched. Please appropriately connect the nodes using edges and specify the direction of each edge. Label each edge with a destination architectural register and the corresponding tag. Okay, let me give you some hints on how you can start solving this so that you don't, let's say, fall into the trap of going into loops of trying to figure out which are the registers. Okay. So let's start with something. So the first thing you should do is try to find out what are the simplest instructions which do not depend on anything else, right? So let's see here. We have an addition, right? What is the tag of the addition? It's Z, okay? And to which tag does this correspond? It corresponds to R8. What does that mean? Whenever we finish the computation for the tag Z at the reservation station, we'll update register 8. So for sure, the destination register for this add instruction is register 8. Okay. So we know that this one, you can start writing it here because don't go from paper to paper. So it's like, this is R8. And as we can see, there are 2 registers which are valid and their values are ready. The values are 28 and 1. So you need to find out from the snapshot of the register alias table, which registers have the values 28 and 1. As you can see, there are at least 2 registers with these 2 distinct values. This is R1 and R2. R1, 28, R2, 1. Okay, these 2 registers are ready, and which means that there is no computation where these 2 registers are destination registers and they need to be updated. And R8 is going to be updated using the addition result of R1 and R2. So the first thing you could do in the data flow is the following. So start with the most simple one. So you have a node, which is the register R1. Then you have the register R2. And you create a data flow, right? So you have a plus. And what is the outcome of this? The outcome is the tag, which is Z, and the destination register, which is R8. Is everyone okay with that? Okay. Okay, let's move on to the next one. So we solved this one. You can cross this out. We found out this one. Okay, we do not need anything else with the additions, right? Or we might need, but we'll see. Okay, so as you can see, there is a register. So we need to find one instruction then, which was executed before all these instructions, right? As I said, there are 5 instructions, 4 of them are in flight. So there is one which was executed before all of these, right? And we need to find it before we proceed to these instructions, to the rest of the instructions. Okay, how do we do that? We go to the first instruction that was pointed here, right? It's X. And here it says X, which is R5, right? Depends on the value 50, the register number 1, source register, and the value 1. And what can you see here? You can see that R2 and R3 have the values 1 and 50. So what is the catch here? The catch is that if you see in the initial state of the register alias table, R3 did not have the value 50. R3 had the value 3. So which one is the first instruction that was executed before everything? It was the one that updated register R3. Okay, and we need to find what sort of instruction this should be. So from all these values, which values can end up in the result 50? It's R7 plus R4. So only this, there will be distinct values in the exam, so that you will not have a conflict on how you come up with the 50, right? So R3, R4, and R7 end up adding and giving the result to R3. So you know that for sure the instruction add R3 from R4 and R7 is the first instruction executed before every other instruction. So continue with that one in the exam. Let's say that you have here R4. I will leave a gap for a specific reason. Let's keep it R7. And let's do the addition. And you take, here the tag doesn't matter because it's a previous instruction. You can assign the tag in whichever way you want. The result is R3. Okay. Is there any questions up to this point? Okay. So this way, given that we found this instruction, we also know that X is the result of the multiplication of R3, which is 50, and of a valid register with the value 1, which is R2, right? So the next instruction, the first instruction which was executed is this one. It's R5 as the multiplication result of R3 to R2, okay? So this is done before everything, right? And we take R2, multiply it with what? With R3. And as a result, what do we have? Tag X, which is the tag of R5, and the destination register, which is R5. Is that clear? Okay. Then you go and check the next ones. Sorry. I'm sorry. Okay, then we're searching for Y. Y depends on the following registers. Tag X, register with tag X, and the register with value 20. Which one is the register with value X? From the previous step, you go back to your data flow, you see that the register with the tag X is register R5. So for sure, one of the source registers is R5. And then the value 20, and you check from your table. Is there any register with value 20? In this table, we don't see any register with value 20. And we go to the initial table. Do we see a register with value 20? Yes, we see R7. But in the latest table, the R7 depends on value Y. So what happened here? The destination register is the same as the source register. So we use the initial result, the initial R7, but we overwrite R7, right? So what do we do here? We used R7 as a result. We multiply it with X, right? And we end up in Y R7. Okay. So we have, how many instructions do we have so far? The instructions is equal to the number of your nodes, right? You have one node here, 2, 3, 4. We miss one instruction, which is the last one. Miss T. What is the destination register of T? The destination register of T is R9. So for sure, it's a multiplication that involves as destination register, the register R9. And what are the values of the source operands? 23, which is R6, and 50, which is R3. Right? That's pretty straightforward. We multiply R6 with R3, and we get the result in R9. That's why I left some space here. So you get R6 multiply R6 with R3, and you get the result T, R9. So right now we have all the 5 nodes that we need, which corresponds to 5 different instructions. And we need to figure out exactly what, right now we need to go to the second exercise, which says, fill in the blanks with the 5 instruction sequences in program order. There can be more than one correct ordering. Please provide only one correct ordering. When referring to registers, please use their architectural names. Place the register with a smaller architectural name on the left source register box. Okay, so I will ask one question. As we saw, R1 and R2, we add them and we end up in R8. Okay. The question is, can this be the first instruction? Why can it be the first instruction? Sorry? So I'm saying that we saw that adding R1 and R2, we end up in R8, which is independent of the rest of instructions. Can it be the first instruction? If it can be the first instruction, then when do we add R3 to our, when do we come up with the result R3 from adding R7 and R4? Is that possible? Like the result of R3 is not in the reservation stations. So this is not possible. If you add first R1, R2 to the destination register R8, it's wrong. That's not possible. Because we don't have the previous instruction, which is R3 from R4 and R7 inside the reservation stations. So don't be confused with that. The first one is the one that doesn't exist in the reservation stations, which is add R3, R4, R7. After that, you can place this one that I mentioned, add R1, R1 and R2 to R8. This you can place it anywhere you want, but it cannot be before this instruction. Okay, so for example, I can do here, add R to R8, R1, and R2. Okay, so what's the next one? The next one we need to do is we use the register R3 and the register R2 to come up with a result in R5. So it's a multiplication. The result is in R5, R3, and R2. I mean, yeah, the opposite way, because it's not important, but yeah. And then, so we did this, we did this. Basically, let me color it differently. So we did this, we wrote this one, we wrote this one, we wrote this one. Then for sure here you need to keep the order correct, right? The order should be correct. Do not mess up the order between the nodes because R7 depends on the new result of R5, which means that the multiplication is stored in the register R7, which is the Y. And it's the result of the multiplication between R5 and which one? R7. And the last one is the multiplication between R6 and R3 in R9. This instruction and this instruction, from what we explained so far, can be placed anywhere after this instruction, right? Why? Because the operands are not used, the destination registers are not used as results in any other instruction. That's it. I think if you were able to like concentrate a bit and check quickly which are the easy instructions to determine, then it will be an easy question. Thanks a lot.
Okay, the next question is about GPU and SIMD. So this is actually one of the common questions in our exams, that you need to calculate the SIMD utilization rate. So yeah, I will quickly go over the question. So we define the SIMD utilization of a program that runs on a GPU as the fraction of SIMD lanes that are kept busy with active threads during the run of program. So, and we usually, I mean, we should calculate it at the end of the application, not in the meantime. So usually we have a code that you need to analyze it. So here in this code, you can see that this is actually a C code that's gonna be basically offload on a GPU kernel. So you have a for that the number of iterations is 1024. And in each iteration, we have several instructions. So we have first this simple instruction. Then we have an if condition instruction. There are also some instructions inside the if block. And at the end, we have this instruction, right? So the total number of instructions inside the for loop is k plus 3. So we are about to actually offload each iteration to one thread. So since we have 1024 iterations, means that the number of threads that we need is 1024, right? Okay, so now let's see the questions. So the first question is that how many warps does it take to execute this program? So we know that basically the warp size is 32 threads. And since we have basically, so the number of warps would be the number of threads divided by warp size. So we have, as I said, 1024 threads, and each warp is 32 threads, which means that we have 32 warps. I guess it's clear, right? Okay. I mean, usually in these questions, the first part is so easy, but it gets a bit more complicated. But this actually last year was quite easy. Yeah. So in this example, yes. So yeah, the number of threads per warp is equal to number of SIM delays. Yeah. So in part B, we are saying that assume that the condition for the if statement is I mod 16 equals to 0. Then we are saying that what is the number of instructions k in the body of the conditional block? Basically, we want to understand the number of instructions inside the if block such that the SIMD utilization is 11/32. Okay. So we need to actually calculate the SIMD utilization parametric with the k and then try to solve the question. So usually when you want to calculate the utilization rate, you need to see basically the number of active threads divided by ideal number of threads. Okay. So our if statement is I mod 16 equals to 0, which means that in every warp, there are 2 threads, thread ID 0 and thread ID 16, that they will take this branch. Other than that, they will actually, they don't enter the if block and they go to this instruction k plus 3. So in every warp, there are 2 threads that they actually take or execute k plus 3 instructions. And the rest of threads in every warp, which is 30, execute only 3 instructions. This one, if instruction, and this ci equals to blah, blah. And the ideal case that we want is basically we want that all 32 threads actually execute k plus 3 instructions. So this equals to 11/32. So you can easily cancel out these 2, and then we have this 2k plus 3 plus 90 equals to 11. And then we would have 9 equals to 90, which means that k is 7. Is it clear? I mean, the key point is to come up with this equation, which is which is not hard to come up, because so we know that because of this if statement, all warps are the same. The only difference is intra-warp, that some threads actually they take the branch, and other than that they don't. So you can actually write the equation only for one warp, because all warps are the same. Okay, we will repeat this again in the next one also. Okay, so part C is a bit harder than part B. So we just changed the if statement, is saying that we will enter the if statement if I mod 16 equals to 0, and the same, and I is less than 512. So with this if statement, we understand that basically if the thread ID equals or greater than 512, we won't take the branch for sure, right? Which means that the first 16 warps, they may run inefficient because some of the threads inside the warps, they may take the branch. Some of them they won't. But the last 16 warps, they won't actually, they will run fully efficient, because none of the threads would take this branch. So when you want to write the equation here for this new equation, you need to actually consider different warps. So there are 16 warps in the end that all of them have 32 threads, and all thread actually they run all 3 instructions. I mean only 3 instructions, because they run this, and since they don't take the branch, they only run the last instruction. But there are some warps, I mean the first 16 warps, that they have some inefficient runs. So we can say that there are 16 warps that in each of them, 2 threads execute call plus 3 instructions, and the remaining 30 threads, they run 3 instructions. And here we would have said, okay, we have 16, I mean the last 16 warps, they have, each of them, they have, it has 32 threads, and all of them run 3 instructions. But the difference is here. So we want to have 16 warps, each of them 32 threads, times co plus t3. So this is equals to 5/8. So then we need to solve this equation. So we can cancel out 16. And we can also cancel this 8. This is 4. This is 4. Then we would have, okay, I guess I think right here, 96 plus 2 plus 3 plus 90 equals to 560 plus 20 plus 3. Then we would have 18 co plus 3 equals to minus 60, which is so then this is 7, and then co is 4. Is it clear? Okay.
Okay, so the next question is about branch prediction. In here, we have some information about the system, so I will mark them as we read. Wait. Okay, so we know that the processor implements an in-order pipeline with multiple stages, and each stage completes in a single cycle. And it only stalls after we see a conditional branch instruction, and in other times we just complete all instructions without stalling. So here we have a code. So in here we see 2 loops, and in one
The loop depends on the value of this register, which is R1. And we subtract 1 from R1 in each loop, in each iteration of the loop. And we check if it's greater than 0 or not. If it's greater, we go back to loop here. And the second one is not important because it's not conditional. So in here we have a table with the results for some R1 values. We know how many cycles they take to complete. And the first part of the question asks, first, how many stages are in the pipeline? And second, how many cycles does a conditional branch instruction cause a stall? So let's give them some letters. So this one should be called D to be consistent with the solution that you know. Okay, so we can now formulate the number of cycles that each of these will take. So let's say C is the number of cycles. So we know that the first instruction will complete after it goes through the pipeline. And since each stage takes one single cycle, we will get the result of the first instruction in P cycles. And the rest will take one cycle each, since this is pipelined. So other instructions, let's say the total is I, will take this many cycles. So this is the number of cycles that we would get if we didn't have any stalls. And let's say that we have B as the number of conditional branches. So each time we see a conditional branch, we will be stalled by D. So that's the final formula for number of cycles. So when we check this table, we can put like some numbers in place. So let's first do R1 equals 2. So we know that this loop will execute 2 times because we subtract 1 in each iteration. So we know like, okay, so we can write the numbers in place. So it takes 71 cycle. We don't know the number of stages, so it should stay as is. And we know how many dynamic instructions we will execute. It's also stated in the question, which I cannot right now see, but it should be 50. Okay, so here, right. And so let's write it there. And we know B is 2 because for R1 equals, oh, it's not seen. Okay, sorry. So for this one, we know that B is 2, which means that this is written as this. And let's write it for R1 equals 4 as well. So similarly, we can write this. And we can solve the system and see 2D is 12. And from that, we get that D is 6. And when we put this in place in any of these formulas that we know, P is 10. So do you have any questions? Yes. So it should be always given because then you wouldn't be able to put I in place and you wouldn't know basically. Or we would say if it's like a, I guess it's always given, yeah. Or otherwise you could deduct it if it ends without an outside like interrupt. So in this question, we say that we need an external interrupt. That's why it's given. And yeah. Okay. So, right. And the second part of the question. So in here we have a Mr. Branch predictor that we don't know how it operates. So this means that for some of the branch instructions, we would get no stalls. For some, if we have mispredictions, we would still see stalls. And in here, we have this here for R1 equals 4. We know that with this new design, the program executes in 77 cycles. And okay, to compare it to this, so here we know that it took this many cycles, 83. So basically the difference between both cases is that in one of them we didn't mispredict one, we didn't get the stall. So we know that the difference between these two cases is 6, which is equal to one conditional branch instruction causing a stall, right? So we know that in this case, we could predict one of the conditional branches correctly. So let me write it here. We had in total 4 conditional branches for this input. So 3 of them are mispredictions and 1 is correct. Okay. So in here, the question says, it gives like different predictor designs, and we are evaluating if it's possible to see this outcome with these different predictors. So the first one is static branch predictor, which we have always taken or always not taken. The answer for this one is yes, because in here, like you said, okay, like let's first write the outcome of this. Like we know that the first, okay, from here, when we give 4 for R1, we know that the first branch will be taken because this is correct, and the second one will be taken, and the third one will be taken, and the last one will not be taken. So we know that with this and this, we should be able to evaluate these predictors. So let me copy that here. Taken, 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 not taken. And so in here, the answer is yes. And when we see, if we predict always not taken, we will have 1 correct prediction, right? So yeah, this one should give, oops, this one should give the same outcome. And for B, we have last time branch predictor for, again, the same outcomes. You can see that if we predicted what was the outcome of the last branch in any time here, we would be able to guess like 2 of them correctly, at least, regardless of what we predicted this time. And you could also guess this one correct if you started with taken. So we wouldn't be able to get like 1 correct prediction and 3 mispredictions. So the answer for this is no. And for and for C, we have backward taken, forward not taken. So for this one, we again need to go back to the code. So for this loop, what we have as the address of this, the target, like the destination of this is backwards. So considering this, if we predicted backward taken and forward not taken, we would have said for this loop, it should be always taken, right? This would give us like, for this taken, taken, not taken, we would be correct for these, and we would mispredict the last one. So this would also give 1 correct prediction and 3 incorrect predictions. So this is also no. And for this one, as you can see, we would be able to get this outcome because again, for this, backward not taken is basically it would end up predict the not taken, not taken, not taken, and not taken. And this would give the correct one, which also is the outcome that we are looking for. So this is yes. Okay. Do you have any questions?
Okay. So I guess we are done with the main part of the exam because this one is a bonus question. Oh, I guess we will have another question from the main part of the exam, right? Okay. So what I observe in the past years is that many students do not actually solve these bonus questions. It's partially related with the time not being enough for some students, but I'd like to mention that you never know where the easy questions are, so please check bonus as well. So this is one example that we have quite a straightforward question. So this is about data prefetching, and as you can see, we have, can I zoom in here? Oops. Yeah, we have this kind of access pattern here, right? So it first goes like A plus 1, A plus 9. It goes like this. So if you look at the stride in this access pattern, you access address A, and then, so this is a cache line address. And then you immediately after that access the very next cache line, A plus 1. And then you jump by 8 cache lines and access to A plus 9. And then you do again like stride of 1 and stride of 8. So it goes like 1, 8, 1, 8, 1, 8. So we already know this access pattern. And we also know like what kind of prefetchers are implemented in a system, and we want to calculate some metrics based on those, basically. And for those metrics, you already have the formula, how you calculate them here as well. So, okay, I don't remember the first question, let me read. So you design a stride prefetcher that observes the last three cache block requests, and based on like what you have, okay, so yeah, so it observes the last 3 axes and tries to find a what's it called, constant stride between those axes, right? So if you don't have constant stride, basically you don't do the prefetching. It's a way of building confidence, basically. And as you can see, the stride keeps changing at every axis here. So basically, this kind of prefetcher would not issue any prefetch requests. So the question is asking about the coverage of prefetch requests here. So it means like the coverage means here like total number of prefetch requests used by the program over total number of main memory requests without the prefetcher. And as it will not issue any prefetch requests, the answer is 0 here. I'd like to show you the answer sheet as well. So as you can see here, we don't just put 0%, we also provide an explanation. So if you just put 0% for this kind of question in the exam, it's very likely that you will not get any points, even if the answer is correct. So please, as it's stated in the question, show your work. Sorry, here. Yeah, show your work. Please show your work. Okay. So the second bullet point is here you design a, so you design a n block prefetcher. So for every memory request, basically when you access A, you prefetch the next n cache lines, like A plus 1, A plus 2, A plus n. So the question is asking, what would be the coverage of prefetching if you set this n to 2? So here, if you remember the access pattern, it goes like A plus 1, A plus 9, A plus 10, things like that, right? So for when you access A, it will create a request for A plus 1. When you access A plus 1, sorry, A plus 1 and A plus 2, right? When you access A plus 1, it will create a prefetch request for A plus 2 and A plus 3. So you will have this kind of prefetcher. So let's check like the percentage of like how many of these prefetch requests are actually useful. So once you have A, you already access A plus 1 in the feature, right? And prefetching A plus 1 is something useful, basically. So this is a successful prefetching, right? And you also prefetch A plus 2, but you never access it in the access pattern, so you never use it. So it's not good. And if you just simulate this a little bit, you will see that actually 50% of your prefetch requests become useful. So the coverage value becomes that. So let's move to other parts. So here, as you create prefetch requests, you will have more memory accesses, and it will eat up from your available memory bandwidth. So here we are questioning that. So again, if we have n set to 2, what would be the bandwidth overhead to the system? And here also you're given a formula. So you need to basically calculate the ratio of number of main memory requests with the prefetcher over number of main memory requests without the prefetcher. So this is very clear here. So if you simulate again, okay, so there is something that we need to highlight here. So if multiple prefetch requests are generated for one memory address, only one request goes to the DRAM. So you have a prefetch request for, let's say you access A, right? And then this creates a prefetch request of A plus 1, and then an A plus 2, right? So later in time, you need to access A plus 1, right? But you don't create this memory request because you already prefetched A plus 1. So you don't have to do this access, right? Or in other words, so you access A plus 1, either via prefetch or normal request. This will result in like A plus 2 and A plus 3. So you can see that you have 2 A plus 2s, 2 A plus 1s here. So for those, you will perform one memory access. So if you simulate this like this, you can see that for every 2 memory requests, we will actually end up having 3 memory requests because of the prefetcher. So that's why actually this overhead in terms of this metric becomes 3/2. Okay, sure. Yes, so yes, you're right. Yeah, I actually wrote it here. Yeah, there's a mistake here. Thanks for highlighting that. So when you access A, the prefetcher will get A plus 1 and A plus 2. And when you need to access A plus 1, you will have that in the cache. And your next access will be going to A plus 9. And then this will prefetch A plus 10 and 11. Yes, yes. So it's like one hit, one miss, yeah. And then at the end, you will again get like 50% here. Okay, yeah, thanks for the reminder. Sorry, correction. So, okay. So we want to have, okay, now we are in this question. So now we want to have 100% coverage, meaning that by performing prefetchers, we want to get all the data that we want to access in the future. Again, our access pattern is the same, A plus 1, and then A plus 9, and then A plus 10. It goes like this, right? So I want to have a prefetcher that will successfully prefetch both this and this and this, right? Ah, sorry. Yeah. So when I access A, I want to prefetch A plus 1. And when A plus 1 is accessed, I guess in this case, we also assume if it's accessed from cache. So it's basically a memory access. I will get access to A plus, prefetch A plus 9 as well. So to do that with this kind of prefetcher, we need to set n to 8 so that we can prefetch A plus 1 within the prefetches for A and A plus 9 within the prefetches for A plus 1. Okay. Yeah, so so again, this is the bandwidth overhead calculation that we have for this new prefetcher with like n of 8. So here again, we need to simulate. I will not simulate, actually, it's already written here. So you can consider this like for a memory access, how many prefetch operations I will have. So when n is 8, so with prefetcher, you will have one memory access, let's say the real access, and 8 prefetch operations, right? So so this is like basically what changes with the prefetcher. And if you look at this, so accessing A will prefetch all these A plus 1, A plus 2, up to A plus 8. And then once you have A plus 1 access, this will create prefetch for A plus 2 to A plus 9. And some of these will not be repeated because these are the same addresses. So you can see that when you simulate for this particular access pattern, when you have when you access 2 different locations, you will end up having 9 accesses. So it's 9/2. So yeah, and this is the end of this question.
Can you hear me? Yeah. Okay. So this was the last question in the exam last year. So the question is about cache reverse engineering, and it's a pretty long question, but with the right technique, you can solve it easily. So the question goes like this: you are trying to reverse engineer the cache associativity of a new release system. You already know that the cache has FIFO replacement policy and 8 blocks and a block size of 4 bytes. So we'll start with an empty cache, and then the application accesses 5 byte addresses in the following order. And this is the order of accesses that we have. So what do we do with this? So we assume that you can access 3 more addresses after this access, and then observe the cache hit across these 3 accesses. So this is the premise of the question. And so the first question is, which 3 addresses should you access in order to identify the set associativity of the cache? So the options are 1-way, 2-way, 4-way, or 8-way. And we can have multiple solutions in this question, but we have asked for the lowest possible addresses that can enable the identification of set associativity. So so the thing is, we need to provide the answer in detail. We need to give every step, and then that will fetch the full points. So now that we know, these are the things that we know: the FIFO replacement policy, 8 blocks, and block size of 4 bytes. So with 8 blocks, we can have these 4 associativities. So the way we should solve this question is to basically look at how we can look at the state of the cache after these initial 5 accesses. And for that, I will write the associativity. So I will initially write 1-way. And okay. So then I'll also have 2-way. And then 4-way. And finally, the 8-way associativity. So here, the boxes represent each cache block, and the cache block size is 4 bytes. So let's see what is the state of the cache. And here I will just represent each block with the starting address, which can be of the starting byte address. So here you can store 0 to 3, 4 to 7, 8, 12, 16, 20, 24, 28. And then in the first one, you could also store 32, and it goes like this. So here you can store 0, 4, 8, 12, and then 16, 20, and so on. And here you will have 4, 0, and 4, and then 8, 16, 24, 32, like that. And the other byte addresses can be stored in the second set. And here you can store all these addresses that you can access. So let's look at the state of the cache after the first 5 accesses. So you have 2, which falls into the first block. So you have 2 here. Then 9, which is in this block 3, whose starting address is 8. So you can store it here. And then 16, 25, And then 33 is again, it can be only stored in the first block. So we need to replace that, and so I'll strike it and make it 33. So next, if we look at the two-way associativity, we'll store 2 here, and 9 goes here, where the starting address is 8. Then 16 goes here, and 25, because the starting address is 24. And then 33 is the address which has to go to the first set. And here we again replace the current block because of the replacement policy, and we replace with the FIFO replacement policy. So this will go, and we'll have 33 here. And then in case of 4-way, we will have 2, 9, 16, 25. And again, 33 is basically going in the first set, and we will replace 2 with 33 because of the FIFO policy. And in case of 8-way, we will store all these addresses without any replacement. So you still have. So now this is the state of the cache, and we will have to access 3 more addresses. So here the trick is to find 3 addresses which can give you unique, which can find unique associativity or unique hit rates across these associativities. So you will have to find 3 addresses which can give 3 hits in one of the associativity, 1 by 3 in another, 2 by 3, and 0. So so you'll have to find the addresses which can provide you these hit rates. And considering that you need to have 3 hits in one of the associativities, the trick is to find basically 3 addresses which are already accessed in this initial 5 addresses that you were that the application access, so that you will always have a hit rate. So we'll start with let's say 2, 9, and 16, or basically the starting addresses of these blocks 0, 8, and 16. If you choose anything in the middle, let's say 4 or 12, you will still have a miss in all these associativities. So with 0, 8, and 16, let's see what is the state, what will be the hit rate in one way. So we'll access 0 again, which means that 33 has to be replaced. We'll have 0, and here I'll just mention the hits and misses. So you'll have 1 miss. Then 8 is already there, so you will have a hit, and 16 is already there, so we'll have another hit. So you will have 2 by 3. And in case of 2-way, so let's access 0 again. So when you access 0, you replace the one of the blocks here. So we had 16 before, so that was the earliest access that came. So we'll replace that with 0, and then which means that hit or miss. So you'll have 1 miss because the address was not there. 8 is a hit because it's already there, and 16 is not there in any of the in the first set. So you will have to again replace 33 so that you can access 16. So you'll have another miss. So here the hit rate is 1 by 3. And then if you go to 4-way, and if we are accessing 0, 8, and 16, so 0 is currently not available, the block in the cache. So we'll replace 9 with 0 because of FIFO. Then so you'll have 1 miss. Then 8 is also not there, so you replace this one with 8. And then 16 is also not there because we just replaced it, and then we'll replace it with 16. So you'll have 2 more misses. So here you will have 0, And with 0, 8, and 16, you can get 3 hits because you already have these addresses or the cache blocks with these addresses. So you get 3 hits. So here we found a unique solution, or found these 3 addresses which can identify the associativity clearly. But if you solve this question further and try to see other addresses, you will also find that you can get the same solution for 0, 16, and 32. But I will let you solve this, but and I will not show it here. But if you, because we are asking for the lowest possible addresses, we will still go with 0, 8, and 16. Any questions? Okay, so yeah. Yeah. No, I think this kind of a question demands such an approach, because we are asking for the 3 addresses and which associativity to identify the set associativity. You can of course use such a solution there, but I think if you kind of look at the sequence, access sequence, you can find out what kind of associativity basically from the sequence itself in those kind of questions. So now we'll look at the next part of the question, which is a continuation of the first part. And here we are asking for what is the associativity of the cache if the cache hit rate observed over the 3 extra addresses accessed in the part 1, where if it's 0, then we are saying, so if it's 0, then it's 4-way. So then 1/3 is basically yeah, 1/3 is 2-way. And 2/3 is one-way solution. So, and 1 is the 8-way. So this is pretty straightforward. You use the solution from the previous question and then previous sub question and get the answer for this. Now, the third question is, when you access the 3 addresses you determined in part 1, you observed 100% hit rate across these 3 accesses. Now your friend asks you to access 4 more addresses in the following order, and you get these 4 other addresses. Which of the above 4 addresses would result in a cache miss? So the key part of this question is that we are given this 100% hit rate information, and we only get 100% hit rate in 8-way solution. So if I redraw the 8-way, the state of the cache after the last 3 accesses. So okay, so this is the state after the last 8 accesses, but now we are given 4 more accesses, and we need to find out what is the which one of these accesses results in a cache miss. And here you can see that there is 32, and there is already a block which is having the address 33, the byte address 33, which means it will be a hit. And then you have 0, and because there is a block which is having 2, you get a hit. 8 is already there because of 9, and you already get a hit. 28 is not there because this block stores 24 to 27. So this one will be stored in 28, and this is a cache miss. So the answer is 28. So that's it. Yeah, for the first part, I think you need to look at other addresses, but the lowest address is the one which we solved here. But this may not be true for other questions. Thank you. Hosong, can you hear us? Hosong?
Hello, everyone. Can you hear me? Hello?
Hosong, can you please wait? We are trying to share the screen.
Hello?
Can you hear us?
Yes, I can hear you.
Yeah, can you
And
please wait for a few minutes? We are trying to
Okay.
set up the screen sharing here.
Okay.
Please go ahead.
Okay. Yeah. So let's first
Can
take
you
a look.
please turn on your camera as well?
Yeah, I think it's not very convenient for me now. So
Oh, okay.
I'm sorry. So yeah, let's first take a look at the question. So we are given a in-order pipeline processor that has the 5 stages in the pipeline, and we have the instruction format that like this, where we have the destination in the first and the 2 operands that follows. So the first question is, what's the ALU's latency for the addition and multiplication command? So we can take a look at the pipeline diagram that shows that corresponds to each of the instruction. We can see that for a multiplication instructions, we have 3 stages in the execution stage. And for all the additions, either the add immediate or add from 2 registers, they all take 1 stage in the ALU. So it's pretty straightforward that the addition takes 1 cycle and multiplication takes 3 cycles. Okay, so for the second question, does this processor implement data forwarding? So the purpose of data forwarding is to forward the results that are needed by following instructions before they are written back to the register files. So we should look at the later half of the pipeline to see whether some data-dependent instructions has already resumed execution before the input data is written back. And we so the first step to do is to find these instructions that have data dependencies. So we find that in instruction 4 and 5. Oops, sorry. In instructions 4 and 5, register R5 is written to at instruction 4, but it's also an input operand in instruction 5. So, and if we take a look at the pipeline diagram, we can see that instruction 5 already starts the execution stage, while instruction 4 is still in the write back stage. So we can say that there's a data, the processor implements data forwarding, and it's between write back and execution stage. Yeah. So the next question is, so we observe in this pipeline diagram, the decode stage, it takes a variable number of cycles, sometimes 1 cycle, sometimes 2 cycles. So one of the possible explanation for this is because we have up to 2 operands that are that comes from the register file, so it takes more cycles to read both operands from the register file, and we can also verify this hypothesis by taking a look at instruction 2. So this is an add immediate instruction, so only one of its operand comes from a register file. So R6 comes from the register file, which will take some time in the decode stage, but 5 is an immediate value, so it doesn't take time in the decode stage. And we see indeed it only takes 1 cycle for the decode stage. Also take a look at the 5th instructions that we just saw, that has the that has one of the data forwarded from the write back stage of instruction 4, and it also takes only 1 cycle. So, oops. So we can, oh wait, sorry. Actually, like this shouldn't impact the number of cycles in the decode stage, because yeah, the result is forwarded from the write back stage, and anyways, but still, like for the second add immediate instruction, we can observe this. So we say that the reason for the variable latency in the decode stage is because of the need to read up to 2 operands from the register file. If one of the operand is an immediate or being forwarded, it takes less cycles, only 1 cycle. Okay. So up until now, is there any question? So feel free to interrupt, and I will just continue to the rest of the questions. Yes. So here, let's have this diagram here as well. So following the previous question, it's asking what is the minimum number of read and write ports for the register file that corresponds to this pipeline diagram. So because if, as we said in the previous question, if the instruction needs 2 operands and none of those are being forwarded, it will take 2 cycles. So this means that it will have 1 read port at minimum, because it takes 2 cycles to read 2 operands from the register file. And for the write port, it has it also has a minimum of 1 write port. This is because, so if we take a look at the write back stages, we can see that let's say here in cycle 12 and also cycle 8, these 2 cycles, we see both the write back stage and the decode stage. They are using the register file at the same time. So this means there's at least a dedicated write port that is different from the read port, so that, yeah, this write back and register read in the decode stage can happen at the same time. So because write back and decode can happen in the same cycle. Okay, so the next question. So can we reduce the execution time of this piece of code by adding more read or write ports in the register file? So first, we should be very clear that adding more write ports shouldn't help performance, because we don't see because like it's an in-order processor, you don't like write multiple values to the register file in the same cycle. But indeed, adding a read port will help the performance, because as the previous 2 questions has shown, if our instruction needs 2 operands that both comes from the register file, they have to be serialized because there's only 1 read port. So first, let's say adding a read port can reduce execution time. This is because we can read both operands from the RF at the same in the same cycle. So now we need to calculate the speed up. So let's have this here. As we said, by adding another read port, basically we reduce the 2-cycle decode stage to only 1 cycle. So what we can do here is just merge all D1, D2s into, let's say, D1, and let's write down this pipeline diagram. So D1, D2 will become just D. E1, E2, E3, memory, write back, fetch, decode, E1, and we still have to wait for the memory, write back, fetch, decode, 3 stages of multiplication, memory, write back. And for the fourth instruction, we have, fetch, decode, wait for wait for E1, wait for memory, write back. For the fifth instruction, we need to fetch, but because of the data dependency, this is only D1, and for R7, for R5, this can be forwarded from the write back stage. So we can execute E1, memory, write back. And finally, the last instructions, we have we can fetch, fetch, decode, wait for E1, memory, write back. So yeah, this is a bit tilted. So let's separate them. Okay, and check if they're aligned. Yes, so with one more read port, we finish execution at cycle 13. So the speed up is just the old number of cycles, 16. So 16 over 3, 16 over 13 is our speed up by adding one more read port. Okay. So for the next question, let's. Yeah. So it asks, is it possible to run the code faster by adding more data forwarding paths to the original pipeline? So let's get the original pipeline here as well. So because as we said, the purpose of data forwarding is to forward the results from the ALU directly to the previous stage of the pipeline without having to wait for the memory and write back stage. So here we are looking for the opportunities that, let's say, once some data comes out of the ALU from the execution stage, we should try to forward it to the next dependent instruction as early as possible. So we observe that, the original forwarding happens at the write back stage. So it forwards the results from the write back stage to the execution stage. But here we can actually start forwarding by, just from the memory stage. Because our code doesn't involve any memory instructions. So the memory stage basically does nothing. So we can basically just move all of these parts one cycle ahead, and this leaves at an execution time of only 15 cycles. So the answer would be so yes, it's possible by forwarding from memory stage to execution stage, and the speed up is 15. Sorry, it's 16/15. Yeah, so this concludes this pipeline question. Is there any question you have about these solutions?
Wait, Hanson, there is one question.
Okay, hello. My question is the stall that we do on the second instruction, right? Like we have to wait so that the memory stage is below the write back stage. Is that we have to do that because it's an in-order pipeline? Is that the reason?
So you're referring to the original pipeline diagram, right? So
yes.
Yeah. Can you say again, like which instruction are you looking at?
Yeah, instruction 2. We are finished with the execute stage because it's an add instruction. But then we have to wait 2 cycles.
Yes. It's because it's an in-order pipeline. So you have to wait before the previous instruction has released the stage you need next. Yes.
Okay, thank you.
Yeah, no worries.
Any more questions? Okay, then thanks a lot, Hanson.
Thanks.
And thanks a lot, everyone. I guess we can conclude today's meeting and wish you all the best for the exam.